So, we will continue with the topic or the module on printed wiring board technologies. This is the 6th hour in this particular topic. So, we have gone a long way in looking at the basic technologies that are required that are needed to be understood by a designer, so that the design for manufacturing term can be well understood, because we are also tagging along with this DFM the DFR, design for reliability and design for testability. So, the goal of this particular chapter is to help you get sensitized to the various process technologies. Here we are covering the basic minimum process technology features, minimum chemistry is discussed, minimum material information is given. Now, if you have after this chapter got some kind of an insight, and if you feel that you need to learn more, there are various books that can help you go through this. So, this chapter will end up with looking at high density interconnects, the sort of ultimate in the current state of the art manufacturing technologies using micro vias and new chemistries. Before that, at this juncture, what I would like to do is to give you a recap of the various samples that we have gone through this in this particular chapter, and that can probably refresh your memories. The first thing that I would like to show you is basically a material here. As you can see, this is a pre-preg material. All of you know this is a dielectric material. There can be various organic resins that can be used to manufacture a pre-preg material. A pre-preg material is very important in the sense it gives the electrical characteristics to your system level printed wiring board, and it can have two components. Essentially, one is the organic resin and the other is the filler. Storage conditions are very important. The next sample that you need to have a look at, probably you have seen, is the copper foil. You can see here, this is the copper foil which gets bonded or laminated with the pre-preg material in the manufacture or during the manufacture of a printed wiring board substrate. So, when you combine these two materials, you get a sample like this. You can see here, this is the copper clad laminate. So, this comes in various thicknesses, right from 0.5 mm to 3.2 mm. The thickness of copper and the dielectric can vary accordingly and according to the required thickness. This can be used as a system level printed wiring board substrate, and it also can be used as a inner layer substrate in the manufacture of multi-layer printed wiring boards. Now, typically you can manufacture a single sided board, as you can see here, in which case the printing or the circuit areas will be on one side of the substrate. Then you can have a double sided board, as you can see here. This is a odd size PCB, typically an irregular form of PCB which I am showing you here, a circular printed circuit board. The reason why this is circular is the product requirement demands this kind of a design and shape of the PCB. Normally PCBs are rectangular, but you can also have these kind of one-off designs depending on the product. You can see that this is a double sided board. The holes are plated. You can see a lot of through holes here, and these through holes are plated, which means interconnections have been provided between one side and the other. Now, you can also have advanced PCBs like this, which I am showing here. You can see that this surface is gold plated. Okay. Therefore, there can be a few system level printed wiring boards which require special surface finishes like this. This is a gold plated printed wiring board, and in fact, if you look at it very closely, this has got mechanically drilled through holes of the order of 0.15 mm, that is 150 microns, and these through holes have been made electrically conductive. That means, they have been plated through hole in these PCBs and they are highly reliable. So, these are used for specific applications. This is a high density interconnect structure. Now, you can also have another kind of high density interconnect structures, as you can see here. This is a 8-layer sequential build up high density interconnect board. You can see advanced packages like a BGA and a flip chip, a lot of QFPs, surface mount resistors have been mounted and both sides have been utilized. And here obviously, from this vision you cannot look at the cross section, but I can tell you that this contains micro vias of the order of 90 microns. Okay. And you can also make boards like a flex circuit. You can see here, this is a rigid flex board, and you can also make a completely flex board. Now, I have been taking you through the various process steps in the manufacture of printed wiring boards. I will also show you some of the samples that have come out through those processes. You can see here, this is a photoresist coated copper clad laminate. The red material dry film that you see here is a photoresist material. Now, this is imaged, as you know, and then it is developed. So, you can see here, after the photoresist process is over, this has been imaged, and then you can see alongside samples where you have specifically plated on the circuit areas, and finally, the material is etched and then you get a complete printed wiring board. So, these samples will take you through the various process steps of the printed wiring board. Today, we are going to focus on the complete plated through hole sequence through videos and slides. Let us begin with the topic on mechanical drilling. Very briefly, we have touched upon this in the last class. Why do we require holes? We require holes because we need to register the printed wiring boards during the manufacturing, because when you build up a multi-layer substrate, for example, when you build up a 4-layer multi-layer board, you need to register each of the layers perfectly using the photo mask and the laminate structure. Therefore, you require registration holes or tool holes for manufacturing. Okay. Then the next requirement is that you may require mounting holes on the PCB, which will eventually go through to the mounting of the PCB on the chassis of a product. Okay. So, holes are required for mounting holes for assembly of PCBs. Stacking holes during drilling. Even during the drilling step, when you are stacking, let us say 3 to 4 PCBs at a time, you require all the laminate structures to be stacked perfectly, so that there is no misregistration or vibration or movement during the drilling process, because if that happens, you are going to break the drill bit, you are going to get a misregistration and you will end up with a wasted laminate structure. Finally, the important thing is you drill holes so that you can create plated through holes, and the post drilling process would be to make sure how well you can prepare the hole wall for plating. So, if you look at the double sided plated through hole printed wiring board structure, the interlayer connection can be established one by a riveting technology, which is very old. So, basically in the area where the hole is drilled, you insert a rivet and then seal the structure, but you can't repair it, and you are introducing or adding more weight to the board. Then the next thing is filling with the solder material. So, you have to pour molten solder and fill the hole. So, these kind of technologies are not being practiced today. The third one listed here, filling with a conducting polymer paste is being practiced in some sectors. So, basically once you drill the hole, you use a conductive paste, typically a paste which contains metallic powders, metallic particles like gold, silver, or a combination of silver, copper and so on, and these are dispersed in a epoxy medium, organic medium, and they are printed by stencil printing or syringe dispensing into the whole wall area, and they are cured, and finally they are polished or basically the extra material is removed and the surface is treated in such a way that the surface is planar after the process is over. Then finally, the technology that we are using today is called electroless copper, which was put forth in a paper by Shipley et al. During 1960s, 1964 to 1967. You can see a number of papers, and this became a revolutionary idea in the electronics industry, because you can deposit a very thin layer of copper by electroless and furthered by electroplating means to get a very reliable hole wall, and then modifications and improvements in these technologies today until today have made this process essential. You cannot think of any other alternative today of making a hole wall conductive by such a reliable method. Therefore, you can only see a lot of research activities going on in this area to probably look at reliability issues, to improve the processes and so on. So, electroless came about later, followed by electroplating to increase the hole wall thickness copper, and today it is a very standard technology. To recap double sided board manufacture process steps, the first thing is the design, then we talked about photo tooling, then drilling the holes, and then making the hole wall ready enough to carry the electroless plated copper, because you have to prepare the whole wall well enough so that there are no debris inside and the structure is perfectly cylindrical. So, it undergoes various cleaning processes, and after that it goes through electroless copper. Then you can image the circuit and then add copper onto those areas where you want specifically more copper thickness to be built. So, that is the circuit pattern that you want to add up, and then you can protect the copper with tin or tin lead. Then you can strip out the unwanted the photoresist material, then you can etch out the unwanted copper and then do suitable protection by using solder mask. You can also use solder mask over bare copper, which we will see shortly today, and then protect the board with the conformal coating or otherwise, and then send it for assembly. Now, I will take you through the process description in much detail, step by step, for a plated through hole double sided board, which is again can be replicated for multi-layer boards. Now, the first step in the manufacture is a panel cutting process, followed by shearing using a circular saw. Okay. So, the laminate comes in these kind of large panels, 1150 by 980 mm panel size. So, you have to handle them carefully, you have to keep it flat so that there is no warpage. So, storage becomes a key issue. No dust should be collected, they have to be protected, because as you know and as we have seen during the earlier classes, that any kind of extraneous material has to be removed later. Now, every PWB manufacturer will have a fixed panel size in his process house, and accordingly the plating bath is fixed, and all other chemical baths are basically fixed based on the panel size, maximum panel size that a company can do. So, it can vary from manufacturer to manufacturer. Now, individual boards, if they are very small, will have to be fitted in this panel. So, if this is the panel area, then you have to fit the individual board designs into these areas, so that you can maximize the FR4 laminate material. You can reduce the wastage. You need to give clearance though, but then you can reduce the wastage based on very good floor planning for your panel process. The common panel sizes are 600 by 600, 450 by 600, 450 by 450, 300 by 300, 300 by 450 and so on. So, obviously, if the circuits are small, it can carry more replicated designs on a single panel. So, you have to spend some time as the manufacturer to fit in the entire panel, the circuits that you have on job. Typically, a 15 mm border allowance is given, as you can see here, and then once this planning is ready, it will go through the entire sequence right up to the etching process is over, including probably the solder mask printing and legend printing. So, a lot of time has to be spent in this initial step. Now, drilling, the board now goes for drilling, and as we have seen why holes are required. It is required for component mounting, interlayer connection by through hole technology, stack location holes through and through during the entire process, and for registration. How do you make holes? You have to use a drilling machine. Typically, for prototyping you can use a manual drilling machine, but in a large volume production you have to automate it. So, you have to use CNC drilling machines, and in some cases companies invest a lot of money on having multiple CNC drilling machines, because as you will understand, drilling can be a bottleneck. If the process flow, if you look at the entire process flow from drilling to the finishing processes, lot of time is spent in the CNC drilling, because it is a sequential drilling, okay, and therefore, you have to examine for quality at the end of each panel drilling. Therefore, a lot of time will be spent, because the subsequent processes are fairly fast. They are all parallel processes, including imaging, etching, solder mask printing and so on. So, you have to use CNC drilling machines. Today, in the Indian context, you can buy a single spindle CNC machine for around 30 to 40 lakhs depending on the make, but then you can have multi spindle machines that can easily go up to about 1.5 crore multi spindle machines. So, instead of having one spindle and doing the job of panel drilling, you can have in the same machine something like 3 to 4 spindles working simultaneously and sharing the job of drilling the entire panel details. Now, we are talking about a laminate which is very tough. Copper is soft, the dielectric material and the resin and the filler are fairly tough. For example, if you use FR4, you have the glass material which is very tough, and the drill bit has to pierce through all of these materials and come back. Now, when you drill, obviously there is going to be a lot of heat generated. The idea is use a good material that can withstand these kind of changes. During drilling, there is a heat produced, and then when it comes out, it is cooled, and again these are very fast processes. Lot of holes have to be drilled in a shorter time. So, the drill bit material has to withstand these kind of environment and the process. Therefore, the most suggestive material is solid tungsten carbide with cobalt inclusions. This is a very tough material, and then it is isostatically pressed when it is manufactured, and then you can in fact repair these kind of drill bit materials for at least 2 or 3 reusages. That means, if a drill bit material breaks, you can resharpen it and then reuse it. So, it is expensive. As the drill bit sizes go smaller and smaller, the cost of drill bit increases. And now the drill bit material, as you can see from this picture here, it has got a shank, a turbo shank, and then you have to operate it at higher speeds. As the drill bit size goes down and down, you have to operate it at higher speeds. So, we are talking about maximum 1 lakh to 1,20,000 RPM if we go down the drill bit sizes. I would like the figure to be shown here in this slide here. You can see there are various formats of drill bits available, but for CNC drilling machine on such a tough substrate, you will use a turbo shank, and these sharp edges you can see here. This is a tungsten carbide drill bit material. So, there will be a lot of length available for this to be mounted, okay, and then you can resharpen it for at least 1 or 2 times, so that you can use the material. Now, a requirement for CNC drilling machine is that in order to increase productivity, you have to stack drill the laminates. Typically, you will use 3 laminate stacks for CNC drilling machine. So, basically, if you look at this picture, there is 1, 2, 3 laminates that have been stacked. They have been secured using a tooling hole. This is the bed of the CNC drilling machine. Then you can see here there is a exit board, and here there is an entry board, and this is the drill entry. Okay. So, assume there is going to be a drill at this particular area. Now, as I said before, because of the complexity of the substrate, heat can be generated. So, you use an entry board typically made out of aluminum, and this aluminum acts as a heat sink. So, by the time the drill bit comes out, most of the heat is removed and the entire panel is not affected. Otherwise, you will see that the heat affecting the whole wall structure, because there is an organic resin which can melt and it can quickly cool and solidify, and finally, you have to make sure that the whole walls are cleaned. So, in order to present a very good whole wall structure, you use aluminum entry boards, and also at the exit, because you do not want your drill bit to hit your granite structure on the XY table of the CNC drilling machine. To avoid breakage, you use an exit board typically made out of bakelite laminate, and you can adjust the depth of drilling, so that you can have the you can prevent the misfortune of having your drill bit broken due to touching the XY table. So, these are some subtleties that an operator, although it can be completely programmed, but then initial settings and procedures have to be followed. So, we will now look at the video highlight of a CNC drilling machine. First thing we look at is a manual drilling machine, just to give you an idea how prototyping can be done using a manual, simple manual drilling machine for printed wiring boards. So, here you can see there is a viewfinder. Here you have the speed setter for the RPM of the drill bits. Here the PCB is placed on the XY table. There is a placeholder for the PCB which holds the PCB during the manual drill. Now, here the operator is showing you how to insert a drill bit material into the drilling machine. So, sufficient height is given during the fixing of the drill bit material. Here again we are using tungsten carbide, and as you can see here the drill bit is protruding. This height is very important because that defines the PCB board thickness for a complete through and through drilling. It can't be a through hole that is partially drilled through the depth of the laminate. So, now you will have the viewfinder and you can look at the pads that require the drilling. At this point of time, the pads are completely covered with copper. You are now centering the pad and then drilling at the center. So, obviously, because it is a manual drilling machine, you can have error. Now, you can see a drill operation is being carried out. Manually, the boards are moved to the next pad. The annular ring is also looked at and centered manually, and then the lever is pressed down to lift the drill bit up at the RPM set for this particular board, and then the process is completed sequentially. Obviously, it is a very slow process, but typically well utilized for prototyping. Now, we will see a very simple single spindle CNC drilling machine. You can from this extend your imagination to huge CNC drilling machines which have multiple spindles. So, here you can see emergency button is there for all CNC drilling machines and all high end manufacturing machines. You have a CCTV, you have a camera which is now loaded to the drill area close to the drill spindle. There is a huge XY table, laminates are fixed at the base of the XY table. You can also do programming using your photo mask to create your own database if you are going to do some kind of a volume manufacturing of a particular design for which CNC CAD data is not available. You can manually program it and then store the data and offload it to your CNC drilling machine for subsequent drilling processes. Now, the data is loaded from your database, and then your CNC machine can actually move to the XY coordinates designated for a particular board. Now, typically in a CAD system, you will generate Excel files for CNC drilling machines, and they will be just offloaded onto your CNC drilling machine. So, make sure you have stacked the required number of PCB laminates. Here what we are showing you is the spindle where you are mounting the drill bit. So, there are certain set procedures, especially with regard to the drill bit material protruding out of the spindle. So, here the technician is showing you what kind of distance or height is required for a stack of, let us say, 3 laminates to be drilled through and through. In some cases, typically after let us say a multi-layer board is finished, you want to do controlled depth drilling. In that case, you have to readjust the drill bit to the required depth that you want, because in those cases you do not want through and through drilling to be done. Now, the RPM is to be set based on the drill bit size and the thickness. So, as I said, as we go down the drill bit size, more RPM is required, otherwise the drill bit will break. Now, once these parameters are set, okay, and then the securing of the laminate is done firmly on the CNC XY table, the drilling process starts. In any CNC drilling machine, you will see that the debris are coming out or dispersed on the surface of the laminate, but they will be vacuum pulled into a collector close to the CNC drilling machine, so that the dust coming from the glass fabric and the organic resin does not spread throughout the machine and the adjoining areas. So, in any volume manufacturing, the company can spend a lot of time and quality control on CNC drilling. Therefore, people have invested in having multiple CNC drilling machines to increase the productivity in the units. Now, once the drilling is completed, whatever be the best process, you will see burrs. So, you have to remove the burrs. Burr is a defect that is protruding out of the drill hole wall. So, the process used to remove the burrs is known as deburring. So, this is the fourth step, as you can see here in this slide. Step 4 is deburring. So, you use entry and exit burrs, you remove the entry and exit burrs that have been formed after the drilling process is over. If you do not remove this, these are going to act as high density areas where your plating can get kind of uneven thickness compared to the hole wall, and you cannot insert your component through this. So, you have to get a very clear hole wall. Now, one of the things that you can do is push the burr inside the hole wall. So, you can use brushing machines that can go through the surface of the panel and push the burrs inside the hole wall. Then later you can clean the hole wall inside by chemical and mechanical cleaning. So, one thing is sure that burrs have to be removed, they cause plating problems. You can use conveyorized brushing machines, like as you can see here, this is a conveyorized machine. You have two sets of brushes that operate, and the board is moved across. Okay. It can be a dry process or it can be a wet process. Wet in the sense you can have water sprayed onto the roller brushes. You can also have some kind of a slurry like a pumice slurry that can be used to roughen up the surface and also remove the burrs. The fifth step is using brushing. Here we are cleaning and roughening the copper surface and removing the copper to the extent of about 2 to 3 microns, in some cases much less. The idea is to provide a slight rough surface so that your photoresist can adhere. We have seen this earlier. Now, for this also you can use conveyorized machines. This is a photograph of a roller brush that is used to increase the surface area on the copper top and bottom surface in the case of a double sided board. The next step is the hole has to be cleaned to take up plating. So, as I said, you can use ultrasonic cleaning, where you can use a mild acid, or you can combine both mechanical brushing and chemical cleaning to make sure that the whole wall is perfectly cylindrical and devoid of all debris, glass fiber, epoxy smear and so on. So, what you will basically see is, after drilling, an epoxy smear or a glass fiber which has to be removed. Smear is basically coming from the melting of the resin during the drilling process and a quick solidification. They can also carry a lot of loose dust particles that come from the drilling. Therefore, if you do not clean up, as I said, you will get a reduced diameter of the hole after plating, because for example, if you have drilled, let us say, a 0.6 mm hole, and if you have not cleaned it, and these debris and fibers etc., after plating will reduce the thickness to, let us say, 0.5 mm. And when you insert a component here later, you will see that the component is not fitting into the through hole wall. So, what you will try to do is force its entry into the through wall, and as a result you will break the plated copper, which will result in a open. The seventh step in the PTH sequence is sensitizing the surface. As I said, we are preparing the hole wall and the copper surface for electroless copper plating, followed by electroplating. So, when you prepare for electroless copper, dip in 30% HCl. So, make sure it is chloride rich surface. So, you are trying to make sure that the surface is wet with chloride ions. Okay. Now, you do a micro etch using ammonium persulfate, which is a microagent used to remove small amounts of copper. You can also use a swell edge chemistry using alkaline KMnO4 to slightly swell up the glass surface inside the through hole wall, but these are additional steps. Now you do what is known as a pre-activation. Dip in a colloidal solution of palladium. Remember, we are introducing a new catalyst. This is basically a catalyst material. Since electroless is a process where we do not use external DC compared to an electrochemical cell where we apply external DC and then there is a cathodic and anodic reaction. Here we are going to catalyze the surface with palladium and use the adsorption property of palladium to attract copper ions from a copper solution, copper 2+ solution, and thereby making the surface conductive. So, this is the essential process of electroless copper plating. Now, what we are doing is there is a colloidal palladium typically represented by this structure here. This has to be adsorbed in the entire surface of copper as well as the through hole wall surfaces. So, imagine a picture like this, what I have shown here, agglomerates of palladium atoms encapsulated in alpha stannic acid as a carrier for the palladium. It is adsorbed, remember here it is adsorbed on the surface. Can I see this picture here? Agglomerates of palladium atoms encapsulated in alpha stannic acid as a carrier, it is adsorbed on the surface. So, this is a key process in the entire plated through hole sequence. It is not absorbed, it is adsorbed. Now, this catalyst will provide a good base for electroless plating. The next step is activation. These embryos now have to be broken, so that the palladium atoms can be spilled over the entire area. In the earlier process you can see they were as embryos embedded. Now, you have to split them individually using an activator material and then they are spread in a monoatomic layer fashion here over the entire copper area as well as the hole walls. Okay. So, this is atomic thickness. So, palladium atom and catalyst is now very well distributed and adsorbed. Now, you do a cascade rinse, do not use a forced spray rinse, it has to be a cascaded rinse. Now, these palladium atoms will catalyze a copper reduction process from a solution containing copper 2+ ions like a copper sulphate solution. This can be a copper sulphate solution. Then you have a reducing agent. A reducing agent will provide electrons, okay, typically something like hydrazine or sodium hypophosphite and so on. These can be used to produce copper in situ which can be adsorbed, which can be attracted by the palladium atoms and then they sit on the surface of the copper. So, you get a good physical bond, but very strong bond that cannot be easily disturbed by chemical reactions except for dissolution of copper. So, you get what is known as a nascent copper atom that is formed during this electroless process. So, remember this process, this is very important because this is how you can make non-conductive surfaces conductive, and in a PCB application it becomes very essential because your whole wall is non-conductive. Your copper surface top and bottom is conductive. Now, you are going to conduct the whole walls and establish a connection between the top layer and the bottom layer. So, this is once this process starts, it is autocatalytic. You cannot you need not stop the reaction unless you remove the board from the solution. So, you can build up the thickness fairly well to about 3 microns or even up to 5 microns. So, the initial layer formation of copper and the addition provided between the copper and the palladium is a key issue in determining the reliability of your through hole wall, and in some sense this electrolysis copper process determines the life of the PCB itself, because if there is failure it can happen at this electrolysis copper. So, the technologies available today are high ended. You can look at various technologies offered by various companies which offer highly reliable electrolysis copper solutions. So, at this point the PTH process ends, and I have given minimum information here regarding the electrolysis copper. You can look at various books for more description on electrolysis copper processes. If you look at this diagram, which will give you more clarity, here you can see the cross section copper and the dielectric, and then you can see that the palladium is coated here from the colloidal palladium solution. Then you have what is known as the copper solution. In the presence of a reducing agent, you get copper 2 plus 2E giving copper 0, and then this copper will now attach itself to the palladium surface, you can see here. So, this bond is very crucial in determining the reliability of the board itself. Now, this is autocatalytic in the sense that you can immerse this copper electrolysis copper plated board into let us say electro copper. So, now you can increase the thickness of the copper. So, what you can see basically here is the red balls indicating that it is electrolysis copper, and the lighter one here shows that the thickness is improved by electroplating copper solution. So, electrolysis copper plating, the rate of deposition we will look at. You have what is known as a low build electrolysis copper, which will give you about 1 micron per hour, very slow plating process rate. Medium build gives you about 3 microns per hour rate of deposition. High build electrolysis copper gives you up to 5 to 6 microns of copper. So, it is a very slow process, and you need to have good care control over process conditions. Example, good agitation, good temperature maintenance, shelf life, concentration analysis of the solution, and so on. Electrolysis copper thickness is not adequate for reliability of the plated barrel. So, if you want something like 12 to 5 microns being built up in the additive process technology that we talked about, then you have to go in for additional plating by means of electroplating. So, here the entire board is now conductive. So, it is now suited for electroplating process. You can add as much as copper you want through the electroplating process. So, the copper thickness final decision is based on the electrical design that you have specified, including the hole wall thickness as well as the ground plane and the top signal layer thicknesses and so on. Two routes are possible in electroplating. One is the panel plating method, the other is the pattern plating method. The panel plating method is used for medium dense board buildup, and the pattern plating is done for high density boards. Now, if you look at a multi-layer board that has been individually prepared, the inner layers, and then you have stacked all the 6 or 8 layers, let us say, and in that you have now drilled a through hole. Okay. Anyhow, the smear is going to be there, epoxy smear. You have to remove the epoxy smear, therefore, you do a desmearing process. Smear, as I said, is because the drill bits become heated, resulting in the melting and smearing of the epoxy resin base material across the inner layer copper surfaces within the hole wall. Now, if you do not remove it, your through hole plating will not connect. Therefore, you use certain chemicals to remove the smear. And as I said, if this is the kind of structure you get after the plating process is over, then you cannot insert your component through this. Now, in another situation where in a multi-layer board you want to make the whole walls perfect for better reliability. Remember, you are having inner layers and these are stacked together. There can be misregistration during the final stack up. Now, if you drill a whole wall, in some cases your inner layer copper can be protruding, in some cases it can be inside. It can also be a situation where it can be inside and it is not protruding. Now, if you do a plating in this area, how do you establish a perfect connection? Therefore, we do compulsorily what is known as a etch-back process. It will expose the copper ends of all the inner layers for better bonding. Once you see the copper ends of the inner layers, you can do electroless copper followed by electroplating copper, and you can get better bonding between the inner layers. How do you do that? You do epoxy desmearing, which means you remove these kind of epoxy smear materials or even the base, the pre-preg material, you remove to an extent that you see the protruding areas of all the inner layers of the copper, including the top. Now, you do an electroless plating as is shown here in a dark red, then you follow it by electroplating. Now, you see at these areas, the junctions, the three types of copper, that is the base copper, electroless copper and electroplating copper are well bonded, in which case you will get a very reliable whole wall compared to areas where if you have the epoxy smear or the epoxy base itself sort of overshadowing the copper inner layer areas, you will not get better bonding. So, you get these kind of pillars, okay, these kind of pillars, and we call this as a 3-point connection, and this will ensure copper to bond copper to dielectric bond as well as the 3 types of copper existing at this point to be reliable, and it can undergo thermal cycling very efficiently without any breakage. It can withstand all mechanical failures, vibrational failures or vibrational effects. So, the etch-back is done by using plasma material, plasma etch-back using CF4 plus oxygen in a plasma chamber, or you can use KMnO4 potassium permanganate to remove these kind of epoxy glass material to the required depth. So, this is a key process in the reliability of a multi-layer printed wiring board. Coming back, panel plating and pattern plating are two important routes to the board manufacturing. Panel, as the name indicates, the entire panel will be plated including the whole walls, whereas in pattern plating only the selected circuit pattern areas will be plated, not all the areas will be plated. So, when do you use it depends on your process step that you have finalized and the thickness that you require for the final circuit pattern. Let us look at panel plating first. You cut the laminate, drill the holes, do a PTH plating including electroless. Now, since it is panel plating, you plate the entire panel. So, this is the important step that distinguishes between panel and pattern plating. Now, you do a imaging of the dry film, close the through holes, plate tin as etch resist, etch using alkaline ammonia etchant, strip off the dry film and do a post operation. So, here you are plating the entire area, then imaging, then using tin as an etch resist, and then you are removing the unwanted copper from the board, and then you are stripping off the dry film. So, at this point you have to watch how it is done in the pattern plating process. In the pattern plating process, you cut the laminate, drill the holes, electrolysis plating is done. Now, you do imaging of the dry film, no tenting is done. Compare it to the previous process. Now, you build up the copper by electroplating method on the pattern areas that you require to add more copper to the required thickness. It could be from 8 microns, you are going to build, let us say 22 microns. Now, you tin electroplate as the etch resist on the pattern areas only, then remove the photoresist, or before that you do the etching using alkaline ammonia. So, the non pattern areas will be removed. Now, you strip off the dry film and do post operations like solder mask, legend printing, edge chamfering, conformal coating and so on. So, to understand when to use panel and pattern plating, you need to look at your board design process steps. In some cases additive technology is required, therefore, you will do pattern plating. In a subtractive process, where if you are very strong in your electrolysis copper process followed by build up technology like pattern plating, then you can go ahead with the pattern plating. But the key difference between the two is that what kind of copper thickness you can build in each of these. In the panel plating process, obviously finally you have to remove more copper. So, your etchant should be well controlled, whereas in the other case your plating should have more control in the pattern plating process to get the required thickness. So, you have to calculate the area on the board and the current density and the final thickness, followed by controlling the parameters in your plating solution. So, we look at the process steps. The first thing is, in the plated through hole sequence process, what we are doing is the image transfer. So, this will give you a very good idea about the entire process steps that I described in detail. So, as you can see, we are doing dry film lamination here. The board is ready, drilled, dry film laminated. Both sides have been dry film laminated here. There is no dust, well controlled conditions. This is the photo mask that is being used for this imaging process. Alignment is done here manually, as you can see, with the hole walls that have been drilled, and then it is sent for UV exposure. So, the exposure machine, as you see, can have a vacuum, it is drawn inside, the light is on, the board is exposed, the dry film is exposed, the latent image is now built on the board. Now, the board is sent for developing. After the polyolefin layer is removed from the surface of the dry film laminated structure, you develop the image using a 1 to 2% sodium carbonate solution. Now, at the end of this conveyorized machine, you will have a water rinse to remove all the excess sodium carbonate solution. Now, you can see that the board is developed. Now, if you want to do electrolysis copper, this is a very essential step. Whether you want to go for pattern plating or panel plating, you will have to do electrolysis copper. What are the process steps? Watch this video carefully to understand the electrolysis plating process in much detail. Now, you have the drilled board. It is now micro etched using ammonium persulfate solution for about 60 seconds. This will remove a few microns of copper. It is a mild etchant. Agitation is very important. In large workshops, you will have conveyorized automated systems. What we are showing is a simple prototyping process. Then it undergoes a water rinse for 30 seconds to remove all the micro etchant that we have used. Now, this is followed by acid dip 10% sulfuric acid solution for about 60 seconds to neutralize all the etchant, if any, that is present on the surface as well as in the through hole. This is followed by a water rinse. So, you can see after any chemical dip we do a water rinse, because there should be no transfer of one chemical from a tank to the adjacent tank, which can be a different chemical. Now, we are activating it as you have seen in the illustrations in the slides using 10% hydrochloric acid solution. This is for about 60 seconds. Then this is now introduced into the activator or the catalyst, palladium chloride. This is for a fairly large time. Now, what we are showing here is a simple lab type prototyping, but in practice you will see huge tanks in which these panels will be loaded with jigs and then introduced into the palladium chloride solution. So, here time is very important, agitation very important, wetting of the surface is very important. Now, you follow it with a cascade rinse typically, but what we are showing here is a spray rinse, very soft spray, and finally, after this activation is done, we now introduce it into the sequence of chemicals, that is a post activator. So, here as you can see, this will be the palladium atoms will be split, the embryos will be split and they will be dispersed from the embryo, forming a very uniform layer on the surface of copper as well as the through hole walls. Mind you, we are activating the surface as well as the through hole walls. We can't selectively do for the hole walls. So, any process here will cover the hole walls as well as the surface. That will ensure good binding and provide better connectivity from the top copper surface to the bottom copper surface. After the water rinse is done, this is now introduced into the electroless copper plating bath. This is actually shown here as a tray bath, but again in practice for large volume manufacturing, shelf life is very important. So, for a prototyping unit, because this has very low shelf life, only small quantities are used as and when required. So, this contains a copper sulphate solution and a reducing agent, which will reduce the copper at the site of the palladium into copper atoms. So, you can see the color has changed, copper has been deposited on the surface as well as the hole wall surface. This is the very key process for all through hole boards. So, this is now a complete electroless copper plated panel. We will stop here at this point and discuss panel plating, pattern plating, and how the boards are etched to get a complete top to bottom interconnection between two electrical layers in a system level printed wiring board in the next class.